Let's look again at velocity time graphs. Let's look at a case where we have an initial velocity of 0, and at 2 seconds, the object is moving at 10 meters per second. So from this graph, we can determine the acceleration as the slope of the line, and the change in position, otherwise known as displacement, is the area under the graph. So let's say, for example, we have this graph and we want to determine some information about this object, this car, this person, this thing that was moving. We can use our knowledge of the acceleration and what change in position would be to answer questions. So what is the acceleration of the object? Well, we can find that by determining the slope. The final velocity was 10 meters per second. The initial velocity was 0. The final time was 2 seconds and the initial time was 0. That gives us 5 meters per second squared. Now what is the displacement? Displacement would be the area under the graph. I can see that that looks like a triangle, so I'm going to use the equation for a triangle, 1/2 base time height. Since the base is time, I will put time there, and since the height is the final velocity, I'll put VF there. This gives us a final displacement of 10 meters. This works well when we have the graph. What if we don't have the graph? So all motion can be graphed, but we might not be given the graph. So in this case, I have created a generic graph of velocity and time. In this case, this is going to be a very special case. Our initial velocity is 0, and at time t, our final velocity is v sub f. So if I use my algebra skills and evaluate this line, the equation of a line would be y equals mx plus b. So what's in our y position? Well, the y represents the thing that is graphed on the vertical axis, so that would be the velocity. M represents the slope of the line, and in our case, the slope of a velocity time graph is the acceleration. So I'll put A here. And then X represents what's on the horizontal axis, and in our case, it's time. And then B represents the y-intercept, and in this special case right now, it's 0, but we'll just put a V initial here, okay? And this would be our final velocity if we're thinking about it as a line where you have the slope and the time. So we have the slope and the horizontal value, and we have the intercept. Then we should be able to find the final y position, y point, and that would represent our final velocity. So most of the time we don't see this equation written in this order, but that gives us a general equation that we can use, that the final velocity, is equal to the initial velocity plus AT. And so we can use this whenever we have information about the motion of an object, but we don't have the graph. This works only for constant acceleration. Now, what if we wanted to know what is the displacement of an object and we don't have the graph? So let's set up a general equation for the displacement using our velocity time graph. So remember, the area under the line is our displacement, and this one is a little bit special, that our displacement will be the area, which is 1/2 base time height, and just like we did before, we can write an equation for the displacement in terms of our graph. So our area is our displacement, our base is the time, and the height is the final velocity. put parentheses here just so we would remember to multiply. Most of the time, if you see this function, you might see it as 1/2 v final times t. Now this is really important that this is only used again for cases of constant acceleration, and this must only be used if the initial velocity is 0. That's really important. This equation will not work if the initial velocity is not 0. So let's practice using these equations in a case where we don't have the graph given. So a bike starts from rest and speeds up to 5 meters per second in 20 seconds. Determine the acceleration. The important thing to notice here is that starts from rest means that the initial velocity is 0. Now, just like I said before, anything can be graphed, so we could think about the velocity versus time graph showing us it starts from rest, and at 20 seconds, the velocity is 5 meters per second. And so we could sketch our velocity time graph. Now, if I use the equation of the line for my velocity time graph that we determined before, that v final is equal to v initial plus a t, the final velocity, show my substitution, would be 5 meters per second. Our initial velocity is 0 because it starts from rest. Our acceleration is unknown because that is what we're looking for. And the time is 20 seconds. So we'll put 20 right here. So then this would simplify to 5 is equal to 20a. So 5 divided by 20 on both sides would equal a. So the acceleration would be 0.25 meters per second or meters per second squared. So always start with your equation and then show your substitution and then your final answer. So the substitution step is important and the final answer is important. The algebra steps in the middle are important to get correct, but not important to show me when you are solving problems. Now let's determine the change in position of the bike. Again, we weren't initially given the graph. We could sketch it if we want to, but I do know that in general, I can use an equation for the change in position. Now, since this object started from rest, I can use the generic area equation of delta x is equal to 1/2 times final velocity times time. Now remember, this only works if the initial velocity, v initial, is 0. So we have to be very careful to only use it when it's appropriate. There'll be times when the initial velocity is not 0. So here I know the final velocity, I know the time, so my delta x will be 1/2 times my final velocity of 5 meters per second times my time of 20, and then that's my substitution. So then my final answer would be that delta x is equal to 50 meters. So I've shown the equation that I'm going to use, I've shown my substitution, and I've shown my final answer.